but love a bubble? Technically, a bubble is any gas surrounded by a solid or a liquid. It could be a lot of liquid, like the ones made when you open that bottle of water you didn't realize was carbonated, or it could be the thinnest possible film of liquid surrounded by more air. Like these! But bubbles do more than tickle our tongues and delight our inner child. They're cheap, easy to handle, and versatile, which makes them a great candidate for scientific experimentation, too. Over the years, these whimsical wonders have found their way into a ton of research, from human health to sci-fi sensors. So let's take a look at some of the surprisingly sciencey uses for bubbles. Our first example comes to us courtesy of particle physics. Back in the first half of the 20th century, scientists used this nifty tech called cloud chambers. As the name suggests, they were filled with a vapor, and as an energetic particle passed through, it would cause some of that vapor to condense into tiny droplets. Then in 1952, the American physicist Donald Glaser took a look at a cloud chamber and thought to himself, what if we swapped everything around? In other words, he invented the bubble chamber. Instead of a vapor, you start with a liquid inside a pressure-tight container. You then heat it to just below its boiling point. After you've got that set up, a piston built into the chamber pulls out, reducing the pressure inside the container. Since liquids tend to have lower boiling points at lower pressures, the liquid suddenly finds itself above its boiling point. It's still a liquid, although scientists call it superheated, so you know something weird is going on. Whenever a charged particle passes through the chamber, it'll interact with a trail of molecules in this superheated liquid and leave them with a charge of their own. These newly charged particles can then trigger the liquid around them to turn into a gas. And voila, you've got yourself a bunch of bubbles. Scientists can measure these bubbly tracks, like how long and curvy they are, to calculate the properties of that original interloping particle, including its energy, mass, and ultimately exactly what kind of particle it was in the first place. Bubble chambers quickly became a more effective tool than their cloud chamber predecessors, on account of the liquid inside them having a much higher density than a vapor. There were way more molecules for a mystery particle to interact with, so physicists could study particles with even higher energies that wouldn't be slowed down enough inside a cloud chamber. For his invention, Glaser was awarded the Nobel Prize in Physics in 1960, and during the 70s and 80s, a 1,000-ton bubble chamber at CERN helped reveal some of the crucial details of the standard model of particle physics. The instrument was called Gargamel, and it not only unlocked crucial information about the existence and properties of quarks, it helped scientists discover the W and Z bosons, which are basically the particles that mediate the entire process of radioactive decay. Today, bubble chambers are still being used to search for heavyweight particles called WIMPs, which some scientists think could be behind the mysterious dark matter that permeates the universe. However, in other areas of particle physics, bubble chambers have largely been replaced by more high-tech electronic instruments. Not because those scientists secretly hate bubbles, but because the analog technology can't keep up with the high energies of the particles we have left to investigate. But that doesn't mean there aren't other scientific fields where bubbles are able to keep pace with electronics, like computing. Modern computers are typically made from electronic components and work by shuttling around bits of high and low voltage. However, there are certain cases where it helps to have computers that are a bit more fluid. In the field of microfluidics, scientists move teeny tiny volumes of fluid through channels to do chemical reactions. We're talking picoliters here, which are a billionth of a milliliter. The tech basically replaces all the flasks, tubes, and glassware you associate with a stereotypical chemistry lab. And it's useful when you're dealing with incredibly expensive chemicals or want to try a bunch of different combinations. If you're wondering what the heck this has to do with computers, we are getting to that. Traditionally, these microfluidic devices are controlled by tiny valves inside their channels that are programmed and controlled externally. But in 2007, scientists found a way to use bubbles within the channels to not only do the chemical reactions, but control the flow internally. internally. No external oversight needed. The team carefully designed the layout of the channels on their microfluidic device to act like logic gates, which produce a certain output depending on the exact combination of inputs. But instead of the classic voltage variation you find in traditional computing, these inputs come in the form of bubbles. See, when a bubble reaches a junction in a network of narrow channels, a fork in the road, so to speak, it will always follow the path of least resistance, like, say, the slightly wider of the two channels. But if a second bubble reaches that same junction and finds the wider channel blocked by the first bubble, it will have no choice but to go in the other direction. In other words, the team basically used channel thickness to create an and/or logic gate. But with more complex networks of channels, they also designed a full logic family for these tiny bubble computers, including gates, memories, amplifiers, and oscillators. While this approach is about 1,000 times slower than electronic circuits, it's still 100 times faster than the traditional valve-based microfluidic control. Another cool thing is, although the researchers proved the concept using nitrogen bubbles in water, bubble circuits could work with any two fluid phases that don't mix. This means they could be used for so-called lab-on-a-chip devices, which are used in the quest to develop new drugs, for example. Other possible applications for the bubble computers include programmable print heads, devices for cheap but large-scale chemical analysis, and bespoke chemical dispensaries, all places where it helps to combine chemistry and computing into one device. We'll just have to see where the research takes us. But speaking of research, funding. We need that too, so here's an ad. Thanks for watching this SciShow video, and thanks for curling up to watch our videos over the holidays too. Around here, everything is getting colder, so it's the perfect time to sit by the fire with your new Complexly mug and your new Complexly coloring and activity book. While you're at it, throw on a Complexly video and relax with us this winter. All that merch and more is available in limited quantities, so you can get them until we run out. And with each purchase, you are directly supporting Complexly making more stuff. Thanks. We now move from bubbles getting moved around inside a thing to bubbles moving a thing inside them. Because it turns out that an ordinary soap bubble can make a pretty good laser, and it's all thanks to a quirky bit of physics inspired by a cathedral in London. Lasers work by amplifying light rays and collecting them into a coherent beam. In fact, that's what the A in laser stands for, amplification. Usually this amplification is done by bouncing the light between mirrors, but you can also do it by bouncing it around the inside of a curved surface, like a sphere. Doing this creates what's known as whispering gallery modes, named after a strange acoustic phenomenon that occurs inside St. Paul's Cathedral. If you and a friend are standing on opposite ends of the 32-meter wide dome, and one of you whispers, the other can hear you just as clear as if you were standing right next to each other. I mean, doesn't have to be your friend, it could also be an enemy, a complete stranger, parasocial crushes. Possibilities are endless. The reason why this happens is because of the way the sound waves reflect off the curving surface. The same thing happens with light waves inside a curve too. And all these bouncing waves wind up interfering with each other in such a way that they get amplified, just like in a laser. Now, lasers have been made from spheres and cylinders made of glass for decades, but in 2024, scientists showed that a soap bubble could also do the job. The trick is to add a special fluorescent dye to the water that gets trapped in the soapy part of your bubble. That way, when you shine a particular wavelength of light at the bubble, it stimulates the dye molecules and triggers the release of more light. Every so often, a new light ray just so happens to be emitted into one of the bubble's whispering gallery modes, which stimulates even more dye emission. In other words, amplified light. You've got yourself a laser. Now, these soap bubble lasers are a bit unpredictable because as thin as they might look, bubble surfaces actually have a thickness to them. The light will end up bouncing off both the inner and outer sides of that surface. Not only that, but the thickness at any given spot is always changing as gravity pulls the water to the bottom of the bubble. So while you can make a laser, its frequency isn't particularly consistent. Instead of monochromatic light, you get a broad and changeable spectrum, which is hard to interpret and difficult to use for any real-world applications. And eventually it also pops. To solve all of these problems, the researchers suggested swapping soap and water for something called a smectic liquid crystal. You know how some computer monitors and watches have LCD screens that go all like rainbowy when you press on them? Yeah, those bubbles are made of the same stuff. Importantly, with liquid crystals, the bubbles don't have any water involved. This makes them more controllable with a consistent layer thickness. It also makes them less prone to bursting, lasting up to 10 minutes. But what, you may ask, is the point of making LCD bubble lasers in the first place? The difference between using these and solid glass spheres to make a laser is that a bubble is soft and filled with air, and so it's sensitive to environmental conditions. The exact types of light that get amplified ultimately depend on the size, shape, and air pressure of the bubble. And those properties are, in turn, affected by such things as the ambient temperature and pressure. In other words, a bubble laser could be used to monitor pressure changes in an environment, and with surprisingly high accuracy too. I'm talking changes as small as 1.5 pascals. That's about 100,000th the air pressure at sea level. And at the same time, it'd be robust enough to withstand up to 100 atmospheres of pressure without popping. All of this research is pretty new, so the bubbles haven't yet been put to the test in the real world. But the team behind the technology thinks their approach could be useful in the aerospace industry. And on top of that, what works for light could also work for sound. Those whispering gallery modes could come full circle to help scientists create bubble laser microphones. But speaking of sound waves, bubbles have also found a critical role in the field of medical imaging, specifically in improving ultrasound scans. Traditional medical imaging often involves adding something into the body to increase the visibility, or more accurately, the contrast, of whatever structure your device is trying to look at. For example, if you're getting an MRI scan of your brain, you can be injected with a contrast agent containing the heavy metal gadolinium, or you might be given a barium meal before an X-ray or CT scan to increase the visibility of your gut. They gave that to my cat the time that he ate foam and had to get an X-ray to get it out of his tummy. But for an ultrasound, it's a little bit different. Ultrasound imagery relies on sound waves bouncing off an interface between two different substances in the body. It's often used to look at very squishy things like the liver, the heart, and perhaps most famously, growing babies. But sometimes it's hard for our technology to distinguish between all the different squishy things in the body. It can be especially hard to image blood flow with ultrasound, since the lower density liquid appears dark compared to the surrounding tissue, which means you don't have a lot of information to work with. And since blood flow is crucial to telling us how well our organs are working, this can be a bit of a problem. Luckily, scientists realized you can increase the contrast by introducing a different state of matter into the bloodstream in the form of tiny gas bubbles. Now, normally, gas bubbles are the last thing you want inside your body. But in the case of microbubble contrast, which requires less than 2 milliliters of gas in total, the volumes are so small that they don't pose a major risk. Each of these microbubbles contains an insoluble gas and is designed to be about the same size as red blood cells. That way, they can go wherever the blood goes. And with about 1 billion bubbles per milliliter, a little goes a long way. They're also just the right size for the ultrasound waves passing over them to make them expand and contract in resonance. That's the phenomenon you experience when you're on a swing, pumping your legs back and forth at just the right rate to make you go higher. This rapid vibration winds up making the microbubbles super reflective compared to the stuff around them, and therefore making the blood vessels they're inside of more visible. Some parts of the body can benefit from this effect more than others. For example, bubbles can improve the visibility of blood flow to the brain, which is usually difficult to see on account of that big old bony skull getting in the way. Meanwhile, in the liver, doctors can more easily spot lesions caused by things like liver cancer. These can show up on normal ultrasounds, but microbubble contrast reveals lesions when they're much smaller, leading to earlier diagnosis. And in the heart, the fact that the bubbles are in the blood but not in the heart tissue allows cardiologists to clearly see the difference between them, helping to measure things like the volume of the chambers and the condition of the heart walls and valves. But that's not all. By using more intense sound waves to pop the bubbles in a specific area, doctors can time how long it takes for that region to refill with bubbles, giving a read on how fast the blood flow is. Microbubble contrast has become a staple of ultrasound imagery, but it's also being investigated as a way of treating a patient too, as a kind of targeted drug delivery mechanism. This is because the presence of the bubbles makes it easier to penetrate cell membranes without damaging them. So hypothetically, you can put your drug inside some bubbles, inject them into a patient's blood, and then focus an ultrasound beam onto the place you want that drug to be delivered. When the high-intensity ultrasound waves pop the bubbles, the drug pushes into the cells directly where it's needed. This therapy is still in the early phases of research, but the people working on it propose it could be especially helpful for breaching the blood-brain barrier, which is usually very effective at keeping foreign substances in the blood away from the delicate cells of the brain. So hypothetically, bubbles could help us treat things like brain tumors and Alzheimer's without resorting to surgery. These seemingly sci-fi bubble therapies might be just around the corner, but they're not the only super futuristic bubble application being explored. Scientists have recently figured out how to use bubbles to encode and store messages in blocks of ice. Whether it's in your freezer or beneath a penguin's feet, water ice naturally forms with bubbles trapped inside, and those bubbles can either be egg-shaped or needle-shaped. Originally, the team behind this research was just trying to figure out what conditions caused those egg or needle-shaped bubbles to form, as well as what conditions would create ice with no bubbles at all. It turns out a bubble's shape depends on the rate of freezing. The fastest freezing creates egg-shaped bubbles. If it's a little slower, the freezing makes a mixture of eggs and needles. If it's even slower than that, you get just needles. And finally, the slowest freezing rate, less than 3 micrometers per second, gives you clear ice with no bubbles. So if you're a fan of whiskey on the rocks, there's a free tip for your crystal clear ice. By manually controlling the freezing rate of a thin vertical slice of ice, by tweaking the temperature of a cold plate at its base, the team discovered they could create whatever shape bubbles they wanted in whatever order. This allowed them to then try encoding information using Morse code and binary code, assigning layers of clear ice and bubbly ice to either dits and das, or to zeros and one respectively. Binary proved to be more useful since it allowed messages up to 10 times longer to be recorded. In addition, the team found their encoded messages were relatively easy to read. A grayscale image of the surface of the ice shows dark regions where there were no bubbles and lighter regions of different shades for the egg and needle bubble layers. With this information, a computer can quickly decode the frozen message. Now, at first glance, it might be hard to see a practical use for this frozen bubble data storage system, but their paper notes that encoding information this way uses less energy than electronic telecoms, and it can be preserved for a really long time. In Antarctica, scientists have recovered ice cores full of natural bubbles that are more than 1 million years old. For obvious reasons, this particular technology is going to be most valuable in naturally cold places, but that can also include places that aren't even on Earth, like Mars or Europa. So who knows? Maybe thousands of years from now, after humanity has accidentally wiped most of itself off the face of the universe, some alien archaeologist will dig up what they think is a super important message we've left behind, and it's like, Ian Nasir sells terrible bubble mixture. Maybe bubbles will be the messaging medium of a dystopian future, or maybe they'll help elevate us to an advanced civilization based on bubble computers and bubble lasers. But for now, they might just be the low-tech, high-potential, overlooked heroes of the scientific world.